So, we have done magnetic field due to linear currents, straight long wire and then circular current, and from that we derived several phenomena, and we justified why a current loop is called magnetic dipole and so on. Now, today's agenda is to talk about surface currents, magnetic fields, because surface currents which flow on a surface. Let us take a simple example where the entire surface current is in the xy plane. So, we have, let us say, this is, it represents large xy plane, and in this xy plane we have x axis, we have y axis and we have z axis. So, I am making varieties of shapes for x, y, z axis, and that is because we are dealing with varieties of situations. Here this is an xy plane that I am drawing, this parallelogram looking thing. It is in fact a plane which is horizontal here, perpendicular to the plane of the blackboard. The z axis is in the plane of the blackboard, the x axis is in the plane of the blackboard, but y axis is going into the plane. So, try to visualize this plane. This is our xy plane, this is our xy plane, and part of it this way and part of it the other way. X axis is here, y axis positive direction is going into the board, and then x cross y, if you do, you get this vertical z direction. And this is an infinite plane, it is a large plane, there are no boundaries as such for our calculations. So, at the current which is flowing is in x direction, and the current is such, everywhere you have current in this plane, and it is such that if you draw a line in the plane, see line also I am drawing inclined. This line is supposed to be perpendicular to the current direction, it is parallel to the y direction. The current is going in x direction and this is the y direction I am writing. So, if you take a length dl which is perpendicular to the current direction, then we will ask how much current is crossing this line, and from there we define k, which is di by dl, that is the magnitude. If di current crosses the length dl per unit, or the current, if di current crosses this length dl, then di by dl, this is the current density magnitude of that, and this is in x direction. So, we write I cap, and this we write k times I cap, and this is a constant, this is a constant, we take this as a constant. The current density is same everywhere in the x y plane. So, this is our current distribution, and then we need magnetic field at a point above this plane. Remember, I am using the word above because my board is vertical, my xy plane is horizontal, and therefore, I am talking of above, a point above this plane. So, let us say somewhere here at a distance h from the plane, and this point, any point I can take origin. So, I have taken origin, and on the z axis I have taken this point P, where we need the magnetic field. There is no loss of generalization. Anywhere you have a point P and you are asked to get the magnetic field there, from there you can drop a perpendicular, and that point you can take that origin, and x axis and y axis, and the same figure will be there. Now, if I write Barth-Savart law dB, this will be mu naught times mu naught divided by 4 pi, and then for ideal you will be writing k dA, ideal is replaced by k dA, and then cross this r vector and divided by r cube. Same interpretation, you take an element, we need magnetic field due to the entire current in the xy plane, and therefore, we have to take some element somewhere, some area somewhere, and because of this current in this current, this much of current, we will calculate what is the magnetic field here, and this formula is for that. And then you have to integrate properly so that this area covers the entire xy plane where the current exists. Now, it will become simpler if you take the area using cylindrical polar coordinates once again. One simple thing which comes to mind is that this is very good, all x, y, z axis, current is in x direction. So, let us take, we can take this area as, suppose this is a general point on the plane x y, x comma y, then we can say okay fine, we will take dx here and then dy here, and then make a rectangle. This is our area. And then when x goes from minus infinity to plus infinity and y goes from minus infinity to plus infinity, all these areas will cover, the entire plane. So, x axis, y axis, dx, dy. So, this is also possible, but it turns out that when you write all these expressions here, the integrations become very, very difficult. Remember, now we will be integrating with respect to two of the coordinates x and y, So, that double integration becomes quite complicated if you take this. So, what we will do? We will take our area element in a different way. So, how? Let us explain separately. Okay, let me do it here. Suppose this is our plane, this is x axis and this is y axis, and this is our plane, and in this plane we have to take area dA and then vary the parameter, the way we take this area dA, vary the corresponding parameters such that this entire plane gets covered. So, the process is that you take any general point, its xy coordinates are fine, x this and y this, but then look at its cylindrical polar coordinates. Z is 0, the point is in the xy plane, so z is 0. So, you have three coordinates x, s, phi and z, and this z is anyway 0. We are talking of point in the xy plane where we will take the current element there. So, z is 0, and for s and phi, what is s, what is phi? This is z axis, this horizontal line is z axis in this diagram. This diagram and this diagram is different. This I am trying to explain how we can take surface elements in a plane using cylindrical coordinates. So, our x axis is coming out of the board, drop a perpendicular from the point to the x axis. So, that perpendicular will be nothing but this line joining the origin, that is s, this is s, and this line makes an angle with the x axis that we call phi, and z is anyway 0. So, these are the coordinates s, phi, z. Now, if we change s by ds, where do I go? This is s, do not change phi. So, this is s, and without changing phi, change s and reach here. So, this length is ds, this length is ds. Now, change phi to phi plus d phi. So, this is phi and we want to change this phi to phi plus d phi. That means, we will be rotating, this angle will be d phi, we will be rotating and like this. So, this will go here, this will go here, and this is the area we are interested in. This will be our area element. This will be our area element, we make this area element, at this point, and this is the point where my coordinates are s, phi 0, and from here s is changed to s plus ds and phi is changed to phi plus d phi, and you construct this area. Now, if you change s from minus infinity, from 0 to infinity, and change phi from 0 to 2 pi, s going from 0 to infinity, positive values all the time, and phi going from 0 to 2 pi, and construct such areas, you can see that you will cover the entire xy plane. S going from 0 to infinity, s is small, you are somewhere here. You change phi 0 to 2 pi, then that somewhere here becomes here, 0 to 2 pi. So, all this area is covered. Then increase s and then change, then this area is covered. Then increase and again change phi, this area is covered. That is how, if s goes from 0 to infinity, phi goes from 0 to 2 pi, this entire plane will be covered. So, this we will be using in our case. We will be using this scheme in our case. We will not take rectangular dx dy type area. We will take, say, this is our s, this is ds, then this is d phi, s d phi, length will be s d phi, and then like this. So, this is our area element. This angle is phi and then this angle is d phi. So, this length is s d phi, this length is ds, and therefore, the area as such, the magnitude of the area will be s ds d phi, s ds d phi. That is what we need. We do not need any direction on this area, no area vector. So, let us write this dB. Let us write this dB. For that, we have already written this dA here, so that we can substitute. Let us see what is this r vector once again. What is this r vector? This r vector is the vector from the current element to the field point where the field is needed. So, here in our case, it is this vector that I am talking of. This is r vector. This is r vector. If I call this point as A, then it is AP. The r vector is just AP, and as usual, we will do the same thing. AP is AO plus OP. So, AP, which is the r vector, is AO and plus OP. So, what is AO? AO. What is OA? OA length is S and the direction of OA is S cap. So, this AO is minus S cap. OA, this is S in S cap direction, OA is in S cap direction, and therefore, AO is in opposite direction. Then OP, this is O and this is P, this height is H. So, it is H times k cap plus H times k cap. That is this r vector, and the magnitude of this r vector, which is written as r, will be s square and plus h square and square root of that. S square plus h square, square root of that, that will be s. This is hypotenuse, this is 90 degree, and then this, remember, this is z axis. Remember, this is z axis and this is in xy plane. So, z axis is perpendicular to all the lines in the xy plane, and therefore, this angle is 90 degree. This is hypotenuse, and hypotenuse square is this sum of the squares of the two sides of the right angle triangle. So, it is this. Now, we have all the preparations done. What is dB? What is dB? Mu naught by 4 pi mu naught by 4 pi, and then k dA. What is k vector? It is k, which is a constant, I cap. This is our k vector. And what is dA? dA is s ds d phi. So it is s ds and d phi. This is k dA cross r vector. And what is r vector? R vector is minus s cap. So minus s cap and plus h k cap. That is this r vector, and divided by r cube. R is here, the magnitude r is here, cube of that. So s square plus h square, s square and plus h square and 3 by 2. That is expression for dB, the magnetic field at point P, because of this small element on the xy plane. So you can simplify now. This is mu naught by 4 pi. See, there are two variables, ds d phi. You have to integrate with respect to s. You also have to integrate with respect to phi. But nevertheless, let us write this. So this k is there, this s is there, this I can write, this k I have written, this s I have written, ds d phi I will write at the end. Now I cap cross minus s cap, what is this? So I cap is in this direction, x direction, and then s cap is here. So I cap cross s cap, the direction will be in z direction. Okay. In this plane, I can do it here separately. In this plane, which is x here, y here, if this is I cap and here is the point, and then I am saying that okay, this is s cap. So this is s cap direction, this is I cap direction. If I do the cross product, I cross s, that will give me direction in z direction. And how much will be the magnitude of this I cross s? It will be magnitude of I cap, which is 1, it is magnitude of s cap, which is 1, and multiplied by sine of the angle between the two, which is phi. So the magnitude is sine phi, the magnitude is sine phi, and the direction is k cap. What I am writing? This I cap and this s cap, this minus s is still there, this k and this s is this k and this s. So this much and minus s, minus here and s here. So I have written I cap cross minus s cap. Next term, this is I cap here and this is k cap here. So what does it give? I cap cross k cap gives you minus j cap. So it is h here and then it is minus j cap. So minus j cap. That is the numerator. Let's revise. Let's check, cross check. Mu naught 4 pi I have written, this k and this s I have written, this ds d phi I have not written. So let us write ds d phi. So ds d phi is also written. Now it's the cross product business. This k is already written, this s is already written, this minus s is here. Then I cap cross s cap we worked out. This is sine phi k cap, and I cap cross k cap is minus j cap. So it is minus j cap. This is the numerator, and the denominator is s square plus h square 3 by 2. Now integrate. For getting the net magnetic field, integrate. So your B will be just let us write b will be integration of this. Two integrations, one for s, one for phi, and the limits are s will go from 0 to infinity and phi will go from 0 to 2 pi. So, that is this b. This expression is having two vectors, one is k cap here and one is j cap here. Fortunately, they are in Cartesian system. J cap, k cap I am using. They are unit vectors in this y direction and z direction, and therefore, they do not change whether you take your element here or whether you take your element here or here or here or here or here, anywhere. This y direction, x direction, they are fixed, z direction, they are fixed, and therefore, it is a great relief. You can write mu naught here, k here and 4 pi here, that is outside the integration, mu naught k by 4 pi. You cannot take this s out, you have to integrate on s, and then similarly s here. So, this will not come here. So, we will write in two parts, one is double integration, one is for s, one is for phi, and what is there? Minus s square sin phi ds d phi divided by s square plus h square and then 3 by 2. It is like this, and then plus another integration, and this time it is this one. So, this h in fact you can take out, but nevertheless not very. So, this is minus, okay, let me write it, minus h here. So, minus h here, and then double integration of what? This k had been taken, but this s is there. So, s into h. So, s into h, h is written here, s into h, and then you have ds d phi, you have ds and d phi, proper integration limits divided by s square plus h square 3 by 2, and proper unit vectors. This is k, this whole thing is in k direction, k cap direction, and this whole thing is j cap, right. So, this is how we can write. This is there are two integrations. So, the bracket can be here, this much integrate and then put k cap is constant. I have taken outside the integration sign, and similarly here it is this way, j cap is outside the integration. So, that is our this b. What we have done, we have written all these things, we have split this integration in two parts. One is k cap part separately, and that other one is j cap part separately. And then let us integrate this one. Let us first integrate this one. What is this? You have sin phi and d phi, s square and this. So, it is a function of s and phi, but they are not mixed up. The s part is separate and phi part is separate multiplied. S part is s square and then divided by s square plus h square 3 by 2, that is s part, and the phi part is sin phi. So, you can integrate sin phi separately with respect to phi. You can integrate this s square divided by s square plus h square 3 by 2 separately with respect to s and then multiply. So, this is possible because they are not mixed up. If you use x, y, z, then you will not get this benefit. Things will be mixed up and integration will be difficult. So, let us work out this. So, there is some s part and then multiplied by some phi part. And what is that phi part? That phi part is sin phi here and then d phi here. So, S part is all this, all this, all this, that is S part. Phi part is only sin phi d phi. So, this will be of this type. Now, this sin phi d phi integration, as phi goes from 0 to 2 pi, as it goes from 0 to 2 pi, you can see it is minus cos phi, and then you put the limit 0 to 2 pi, and cos 0 and cos 2 pi are same, and then you will subtract. So, this will become 0. So, I do not have to integrate that S part. S part integration is not needed, because that phi part integration is already 0 and it is multiplied by that. So, this part goes to 0. So, I do not have to worry about this. Now, this part. Here the integration is the second integration, this integration. This integration is double integration. So, here also S part and phi part are separate. S it is a function of S and then ds, and then you just d phi. So, they are separate. Once again we can multiply the two parts, S integration multiplied by that phi integration. But if it is something like S square plus H square plus 2 SH cos phi, then it is mixed up, then that multiplication of integrations cannot be done. But here it is simple. So, we can write it as ds divided by S square plus H square 3 by 2, this is one part, and this will be multiplied by integration d phi, that is the other part. S going from 0 to infinity and phi going from 0 to 2 pi, right. So, that is all. This you know, d phi integration 0 to 2 pi will be just 2 pi. So, this thing is 2 pi. So, this is 2 pi times and this integration 0 to infinity and then S ds divided by S square plus H square power 3 by 2. Okay. So, I have done all the complex things which were coming in. Now, this integration you can do very easily. Substitution S square plus H square, this you can write some anything t square, let us say. Then S ds will be t dt, this S ds will be t dt, this will be t cube, this will be t cube. So, you will have that 1 by t square dt. You know 1 by t square dt is very easy to integrate. So, you can do that, put the values and do this rest of the algebra. I will give you the result, and after that this is this integrations, you have to put this integration here, minus h will be there, j cap will be there, and mu naught k by 4 pi will be there, and this integration which is coming, that will be there. You work out that algebra and the result is very interesting. It is in j cap direction, that you have already seen, it is in j cap direction. So, it is B is equal to mu naught then k divided by 2 and minus j cap. Okay. So, this is minus here and then j cap here. Try to visualize this, and let me do it on the table. So, let us say you have x axis, my left to right, here this is x axis, this direction is x axis, and then this direction is y axis, and the entire current is going in x direction, this current is going in this way. Because of this current, I need magnetic field here, and magnetic field is minus j cap direction. k cap is vertical, z axis is vertical. If I have taken this as x axis and z axis is vertical, then y axis has to be on that side, not towards me. So, this is y direction, this is j cap direction, and towards me is the minus j cap direction. So, current is going on this surface of the table from left to right as seen by me, and the magnetic field is coming towards me minus j cap direction everywhere, here, 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 everywhere. The magnetic field, because of this surface current, is towards me, right. So, it is not parallel to the current, it is perpendicular, but then parallel to the plane of the current. It is not this perpendicular, it is this perpendicular, that you should visualize. The other thing is that it is independent of H. The H does not appear in the final expression. So, whether I ask for the magnetic field here or here or here, it is independent of the distance from this plane. And this is because we have chosen, we have done this calculation, this mathematics, assuming infinite spread of this current in xy plane. Normally it will not be there, but once again, if your h is small as compared to the dimensions of the current will be somewhere, it has to loop and then it has to go in closed paths and so on. But the point where you are looking for the magnetic field, close to that, only that contributes significantly. So, if this distance is small, you can still use this equation and you can see that it is independent of h. But does not mean that you go, this is say 1 meter and you go 2 meters above, then this formula will not work. So, these are the kind of things, and your homework is that if the point that we had taken, is not above the plane but below the plane, okay, the current is in xy plane and I want a magnetic field below that plane, that means at a place where the z coordinate is negative. Work out where the change will be. I can tell you the result, and that is it will be plus j cap, mu naught k by 2 plus k cap. Above the surface, the magnetic field is towards me. Below the surface, the magnetic field is not towards me, it is away from me. So, that is the kind of magnetic field a plane surface current produces.